Is the weather forecast trying to save your life, or just ruin your day? You see a 60% chance of freezing rain. Do you drive, or cancel everything? Because a 2-degree mistake turns a wet road into invisible black ice. A 50-kilometer shift in a single snow line? That's not just a forecast error, that's 3,000 cancelled flights, and your connection is gone. A tiny 1-degree miss on a summer day? That can spike a city's power demand by hundreds of megawatts, making your electricity bill jump by dinner. And if a hurricane forecast is late by just 12 hours, 300,000 extra people can get trapped on dark highways. We've been taught to check the weather. But what if the real story is checking the system that makes the weather forecast? Today, we audit the forecast factory. So how do you build a picture of the entire planet's atmosphere, every 6 hours? Step 1, you build the puzzle. Over 100 million observations, or puzzle pieces, are fed into this factory every single day. The big ones come from satellites, giving us that sweeping view. Then you have weather balloons, launched from 900 sites, twice a day, like clockwork, giving vertical snapshots of the air above us. Commercial airplanes are constantly reporting wind and temperature on their routes. And on the ground, radars and weather stations are stitching in the details of the rain and wind right outside your window, while ocean buoys anchor the whole thing at sea. But how do you assemble a puzzle when some of the pieces are lying? That's step 2, the mosaic machine. It's a process called data assimilation, and it's part jigsaw solver, part lie detector. It takes all those millions of measurements and compares them to yesterday's forecast, keeping the pieces that fit the laws of physics and downweighting the ones that look suspicious. Once you have the starting picture, it's time for step 3, the physics engine. These are the models. They run on a grid laid over the globe, with some squares as big as 25 kilometers, and others, for storms, as small as 1 kilometer. And inside each square, the model runs trillions of calculations to push the weather forward in time. But one forecast is just one bet. To really see the future, you need step 4, the ensemble. The factory runs 20 to 50 forecasts in parallel, each with a tiny, microscopic tweak to the starting conditions. Instead of one single answer, you get a distribution of possible futures. You don't just see one bet, you see the actual odds. And finally, the loop closes with verification. Every forecast is scored against reality. The factory learns from its mistakes and tunes itself for the next cycle. 3 different clocks are always ticking inside this factory, and they are always at war. The first clock is global. The big models fire up every 6 hours, 00, 06, 12, and 18 UTC. But for rapidly changing storms, regional models are updating hourly, or even faster. The second clock is latency, the time it takes from an observation being made to the forecast actually showing up on your phone. This can be anywhere from 2 to 6 hours. And the third clock is the refresh rate of the sensors themselves. Radar scans every 5 minutes, satellites every 10, but those crucial balloons only go up twice a day. This forces a constant, brutal trade-off. Do you want a higher resolution forecast that can see thunderstorms, but takes longer to compute? Or a faster forecast that might miss the details? A perfect forecast that misses your decision window isn't a forecast. It's just news. And there are blind spots. Huge gaps over the oceans and parts of the global south mean we rely on satellites to fill in the blanks, but those come with their own biases. And all the while, the chaos clock is ticking. Any small error in that starting picture will double, and double again, over the next few days. This is why specific details fade beyond about 10 days. The factory isn't failing, it's hitting the wall of chaos. But the record shows clear, undeniable progress. Today's 5-day global forecast is as accurate as a 3-day forecast was just 2 decades ago. Think about that. You can plan your weekend with the same confidence your parents planned their Wednesday. And hurricane tracks? The typical 3-day error used to be massive. Now it's down in the 150-kilometer range, That's half of what it was in the 90s. And for right now, in the next 0 to 3 hours? That's called nowcasting. It blends real-time radar with high-speed models to pinpoint storm cells at a neighborhood scale. It's the system that tells you if you need to cancel soccer practice at 6 p.m. because it's about to get drenched. So if it's so good, why does it still feel so wrong sometimes? Where does it break? First, those blind spots. A lack of data over the ocean can seed an error that grows into a massive surprise on day 3. Second, it takes physics shortcuts. If a grid cell in the model is bigger than a thunderstorm, the model has to approximate what that storm is doing. That approximation leaks skill, especially in summer storms and mountain snow. Third is the timing trap. If the updated forecast arrives at 5:05 a.m., but the school district had to make the snow day call at 5 a.m., the forecast failed. Even if it was right. Latency is the hidden killer of good forecasts. And then there's the communication gap. The factory outputs probabilities, the odds. But we crave a simple yes or no. When we misinterpret that uncertainty, we call the forecast wrong. And finally, there's infrastructure bias. We have rich data along busy flight corridors, but sparse data in rural valleys and along coastlines. To be underseen by the sensors can mean being underserved by the forecast. So why does it hold together at all? 2 reasons. First, redundancy. There are many sensors, many models, all constantly cross-checking each other. If one satellite hiccups, others backfill the data. And second, ensembles. They catch the dangerous possibilities hiding in the tails of the probability curve. They are the factory's early warning system for risk. But what's the one thing that changes the entire game? It's getting better initial conditions faster. If you can double the high-quality observations in the 6 hours before a major storm, and process them faster, you can buy 12 to 24 extra hours of useful lead time. And that is the difference between reacting to a disaster and preventing one. So these are the levers they're pulling. For observations, using GPS signals bending through the air to measure temperature and moisture, adding more coastal radars, and even using pressure sensors from crowdsourced smartphones. For cadence, shrinking that window from observation to decision with hourly data assimilation and faster delivery. For communication, pushing ensembles everywhere. Giving you percentages and thresholds, not single numbers. Decision tables are better than sentences. And for equity, investing in the sparse regions, because air doesn't respect borders, and a blind spot in the Pacific can become a disaster in California. Now let's turn the mirror. Here's your playbook. First, use thresholds. Map your big decisions to numbers. If the forecast for wind gusts is over 40 miles per hour, you secure the patio furniture. If the freezing rain probability is over 40%, you delay your trip. Simple. Second, read the whole range. Don't just look at the average temperature. Check the high and low percentiles. Pack for the 75th percentile risk, not the 50th percentile hope. Third, update on the model cycle. For big storms, check for new data around breakfast and again in the early afternoon. Don't get hypnotized by every wiggle on the radar map. And a pro tip, on heat advisory days, pre-cool your house before the peak hours. A smart thermostat can cut your peak bill by 10% on those extreme days. For institutions, it's about standardizing the handoff. They need forecast-to-decision matrices. A utility pre-stages crews if the 24-hour outage risk exceeds 30%. A hospital tests its backup power on heat watch days. They need to buy resources probabilistically, like a grid operator bidding on fuel based on the full range of ensemble forecasts. They need to fund sensor equity, because a new coastal radar protects their region and improves the entire global model. And they need to enforce deadlines. The forecast has to arrive before the decision has to be made. A school closure forecast must land by 5 a.m. A port pilotage forecast by midnight. Period. Let's run the drill. 18 hours until a hurricane makes landfall. The clock is screaming. 1800 hours universal time coordinated. A new ensemble run nudges the storm track 60 kilometers west. Suddenly, the surge risk for a key neighborhood crosses a 10% high-impact threshold. The mayor immediately triggers a prepare message. The hospital begins moving its most critical patients. Midnight UTC, new data from balloons and aircraft is ingested. The model's confidence tightens. The peak winds are now forecast to arrive 6 hours earlier. The utility prepositions 300 crews. The city suspends all-night transit. 6 o'clock Universal Time Coordinated. Nowcasting shows the storm's outer bands are forming faster than expected. The school district immediately pivots to remote learning. The evacuation order is narrowed to only the most vulnerable zones, cutting nighttime traffic by 40%. The outcome? Targeted, earlier moves reduced injuries and shortened power outages by a full day. The factory didn't promise certainty. It priced the risk just in time to act. So here's the final verdict, ledger style. The vulnerabilities, gaps in ocean and polar data. Physics shortcuts for small storms. Latency that makes perfect forecasts useless. A message of probability that gets lost in translation. And an infrastructure bias that leaves rural and coastal areas underseen. But the strengths are powerful. Redundant sensors and models that back each other up. Ensembles that surface the hidden risks. Rapid refresh models for immediate threats. And proven skill gains, decade after decade. This is a system built to learn. Here's your testable takeaway. For the next 3 days, keep a log. Each morning, write down the forecast high, low, and chance of rain. If you can, find the 75th percentile for rain. Each evening, record what actually happened. See how close it was. Then, set your personal risk threshold. Decide now at what percentage you will always act. For the professionals watching, run a latency drill. Pick your single hardest decision deadline and rehearse a full data-to-decision sprint. Measure every step. Shave off minutes until you can reliably beat that cutoff with a clear, ensemble-based decision. In our next audit, we're taking this to the next level. We're going to stress test the electric grid during a 72-hour heat dome, to see exactly how the physics in the sky becomes the price you pay for every kilowatt-hour. If you believe that understanding these invisible systems gives you an edge, then hit subscribe and join the audit team. But first, the red team question, and I want you to be honest in the comments. When was the last time a wrong forecast seriously impacted your day? Was it just a ruined barbecue, or was it something much bigger? Let's talk about it.